Hi, this is Chris Kinberg, and I'm attempting to recreate a BBB recording that should have been made on Friday, the 4th of February, but apparently it failed to materialise. What we're going to focus on today is the use of threads and ways in which a thread can be controlled. And the practical output, hopefully, of today's session is that you'll be able to uh, cut and paste this multi-threaded program into Eclipse and execute it and observe what the output is and make notes of that. So uh, you will remember that we have some understanding of threads from our work on concurrency right at the beginning of the course, and I'll rely a little bit on what we did all that time ago, but I will remind you of the key things that you need to understand. So the principal purpose of this presentation is to learn how to create a thread in Java. There are two main ways, and that is uh, one dash, one raised, one little funny little comma as a superscript. That's by extending the class thread, the system class thread. All right, capital T. And what I mean by extending, as I outlined in the presentation I gave you, I think last week, on an introduction to objects, where I discussed subclassing classes and the relationship between classes, and also how to create an instant of a particular class. So you might, or perhaps you should refer back to that document. It's very easy to read. And the second main way is to implement what's called the Runnable Interface. Well, at this point in time, I'm just going to say that Runnable is a Java system interface, and I shall explain quickly what an interface is. So, um, so what Java is all about creating a class um, for which it might be very, very useful to instantiate any number of objects from this blueprint class. And the object is going to have uh, all the variables and all the methods owned by the class. And I should really tell you a little bit about an interface right now, but I'll postpone that for a few minutes. You'll be able to find more detail about what an interface is in the document called whirlwind.doc that I shall put up on Pharos. So um, let's have a look at the simplest possible way of creating a thread, which I sort of ignored a moment ago. I can give a name uh, to the thread I'm about to create. So my thread, which is of type thread, is going to result from creating a new thread object. So using the Java reserved word new here. So I'm just creating an instance of thread. And this doesn't have the effect of running the thread, it's just creating it. And to run my thread, all you need to do is to use one of thread's method, which is start, and that will start executing thread's run method. So even though we can't see it, there is in the class thread there is a method called run. The method returns immediately. So when you start a thread, you instantly go on to execute the next Java command or the next Java line. It has the effect of starting to run my thread's method, run method. So the next line of code will execute with my thread running in the background. I mean, that's the it's important to grasp that. You've just created a thread, you've just started it to run, and now you can go ahead and run any other commands that you need to run. If a class my other thread extends thread by writing, so that we're looking at the second, well, rather the first of the two major ways of creating a thread. If I define my other thread to be a class which extends thread, and I've got the curly bracket and curly bracket, what I can do in my other thread is to what's called override the run method that I've inherited from thread. I mean, my other thread is going to be a subclass of thread, and I'm inheriting everything from that's contained in thread, in particular the run method. So what I do is that within these two brackets I actually define what I want the run method to do. Maybe it's just to print pretty pictures on my screen. Maybe it's going to handle communications with an internet server. I'm not really bothered what the run method actually involves or what the thread is actually doing. And the sky's the limit, in fact. So overriding simply means you're replacing the definition of a particular method with my own. What inherit means is that you literally inherit as your own all the things contained in the superclass. Okay, so before turning to these matters, I have a rather long aside, and we could, but I'm not going to. I could skip this at the moment. Right at the beginning of the course, we noted that threads can be in any one of a number of discrete states, didn't we? I gave you a following thread state diagram showing you the main possible states, and the thread diagram looked a bit like this. So just to go through this very, very, very quickly indeed. When you use the new operator on a class, you're given a new object. So technically your new object isn't quite yet runnable, but it's been born. It just needs a bit of housekeeping, like the allocation of some memory perhaps to it. But the new thread that you want to run is then put onto the ready queue. It's a queue of threads that are ready to run but aren't actually running. And there may be 100, there may be just 3, it could be any number of ready threads on the queue. And it's likely that what's called the dispatcher will actually pick the thread at the head of the queue, the top of the queue, and allocate it a fixed amount of time to run on the CPU. And the thread changes state from ready to running. And when the time allocated to this thread has expired, the operating system will actually take the thread off the CPU and put it onto the back of the ready queue in order for it to wait its turn to run again. Okay, so if you've got a running thread here, it's possible, first of all, it might want to do some input or output. Maybe it just wants to read the keyboard, or maybe it just wants to send a datagram to the United States, in which case it's going to be kicked off the CPU and put onto, I guess it's a blocked queue of processes. And as soon as the event that particular thread happens, like the input or output is complete, it will be woken up and the thread will change state from being blocked to runnable, because the operating system will actually place the queue on the back of the ready queue, waiting its turn to run on the CPU. If you have a running uh, thread, it's possible that it itself can put itself to sleep for a fixed amount of time, measured in milliseconds and nanoseconds. And when the alarm goes off, when it's slept for a fixed period of time, um, uh, it will be taken off this queue of sleeping processors. It's a bit like a dormitory at night, and the thread will be placed back onto the back of the ready queue again. Okay, if you've got a running if you've got a running process, it might decide to execute uh, a wait uh, a wait method, in which case it's going to wait for a particular event to happen. Okay, and one thing that we'll see that what it might be waiting for is another thread who has got a lock on a resource issuing a notify or notify all method, in which case this thread will momentarily be awoken up, check to make sure a particular condition is true, and then it becomes ready to run, ready to run again. So there's all these different states. The final state is that if you're running a thread, what might happen is that it's finished executing its run method, and hence terminates. It's completed. So the thread at long last just dies a natural death, and any resources that it was using will be uh, gathered back into to be used again, to be reused. So hopefully you remember some of that. Anyway, so if we create a thread with using the reserved word new, it's not yet running, but it's runnable. Right, it's in the runnable state. This means that it could execute if only the Java scheduler allocated it to a virtual CPU or a lightweight system thread. It just needs something to execute. Logically, it's runnable. It can run, if only there was the resource of a CPU, or perhaps one of 6 processor units for it to run on. A certain amount of bookkeeping or setting up needs to be done before a new thread can run, i.e. be made runnable. And typically it's up to the operating system to allocate processor time for it to execute. And what we discussed a long time ago, it seems to me, is though the operating system could decide simply to give all threads a tiny amount of time before taking them off, and before the CPU takes off or removes the thread from running on the CPU, the thread might wish to do input or output, in which case it's going to be put on the queue waiting for I/O to complete. So it's very much up to the individual operating system to allocate such and so time for a particular thread to execute. It's possible that the operating system supports priorities, and if a thread is actually allocated very high priority, that thread might be allowed to run until it actually finishes, or it might be allocated sort of a midway priority of 0.5, in which case if there are any 0.6 priority threads, that will gain some advantage in getting to use the CPU first. And on the other hand, if you've got a priority of just 1, a bit of a tricky situation, because if there are always incoming threads with a priority greater than 1, you might be starved of the use of the CPU. Anyway, the operating system can provide what are called real CPU cycles. In other words, some genuine slots on the real CPU. An old Java 1.0 keeps a running process active until a higher process thread awakens and takes control. And other thread systems give each runnable Java thread a fixed small time slice called a quantum to perform part of its overall mission in life. And when the allocation of time expires, the operating system gives another thread the opportunity to do some work on the CPU. So it's a general question: how are Java threads managed in your operating system? You might have a Unix machine, or you might have a Mac, or you might have a Windows 10. And if you don't know, well, you could just find out simply by Googling the question. And how does your operating system manage kernel threads? So it's possible that a Java scheduler, a bit of software that takes a thread and allocates it to something possibly abstract rather than a real machine, allocates them to a virtual CPU. And I don't really want to go into lightweight Solaris threads, for example, but it's if you're looking at the subject seriously, then you'd probably want to do that. So, as I said right at the outset, each thread can be assigned a priority between the minimum priority, which is 1, and the maximum priority, number 10. And the programmer can set this priority. I mean, it might set a thread to run with sort of medium to low priority because it's not terribly important. As long as it does get the work set for it done, that's okay, that's acceptable. So informally, threads with higher priority are more important in some sense to a program and should be allocated CPU time before threads with a lower priority. And most platforms support time splicing of threads. And this is, again, something that we looked at in the session that most of you missed at the end of last term, CPU scheduling, different scheduling algorithms. So if you're trying to get a good all-round grasp of some computer science topics, you should refer back to that. Most platforms support time slicing of threads, and each thread is allocated a fixed quantum of time, and other things being equal, each thread assigned a CPU or a virtual CPU, or a virtual CPU is just some software that's capable of looking at, say, Java commands and executing them, although that's not being done on a real CPU. I mean, what will be put on the CPU is this piece of software that's capable of interpreting Java instructions. It's like a Java virtual machine. Or processor if there are more than one processor in the system, and will run until that quantum expires. Without time slicing, each thread belonging to a set of equal priority threads will run to completion. I suppose that's the natural consequence of not having time slicing, but having a set of threads all with exactly the same priority. One thread will run after the other, depending on which is picked first, and however long that might take. A running thread might be preempted, i.e. kicked off or booted off the CPU, if a higher priority thread enters the scene. In this case, the preempted thread will simply be made runnable by putting it on the back of the runnable queue. And the thread scheduler's task is to keep the highest priority thread running at any given time. So having said all this, a thread might be removed from the virtual CPU or the CPU if, for example, it, it executes its yield method, which simply means that it gives way to any other queues on the ready queue, or it might be booted off the CPU if it wants to perform input or output. In these cases, a running thread will become blocked, and what this means is that it's neither running nor runnable. And hopefully the thread state diagram that I've shown you above will make much of these state changes clear. A thread is in a blocked state when any one of the four following events takes place. The thread's sleep method is invoked, specifying a period of time when it's not to run, but it's just waiting, sleeping in its comfortable bed until it's woken up. Or suspend is called, which is going to suspend the operation of the thread. And even though it's not fully approved these days, suspend has an inverse operation called resume. So technically, a thread could be suspended for a particular period of time, or where a particular set of circumstances are involved. I mean, maybe resources are running out, but it could be resumed if those resources are replenished. Or thirdly, a wait operation is called, and typically this is going to be involved in a situation where not waiting to use a particular resource could cause a lot of danger. What I have in mind is a non-shareable resource, or a resource which is it's got to be handled very, very carefully, and a thread could be waiting until it's notified that something in the system, some state of the system has changed, and it should wake up and check to make sure it can actually do what it intended to do. And I've got an example which I'll quickly discuss at the end of this talk. Fourthly, a thread might call an operation that is blocking on input or output. And I mean, all along, when I introduced streams, and when you're outputting data through a gateway, stream gateway, you might find that the operation does take time. For example, just writing a single byte onto the internet does take a time. If you're writing 50 bytes, one after the other, maybe the thread that's doing that operation will block because it takes time, and you don't want to hog the CPU if another thread could be doing something purposeful on the CP during that time. And an operation will not return to its caller until the I/O operations are completed. So it'll be unblocked. A thread might be unblocked when the I/O operations are completed. And you might ask what is meant by blocked, and all I mean here is that it's neither runnable nor running. It's in a sort of limbo state. So when a thread is blocked or dies, another thread is scheduled to run in its place. When a blocked thread is reactivated because, for example, it has finished sleeping all the required number of milliseconds, or because the I/O operation on which it was waiting occurs, the blocked thread will start to run again by being made runnable. This means, of course, that the thread yet again changes state. So a quick review of some of the methods found in the thread class, which are all inherited by thread subclasses, are the following. Is alive. You can test to see whether uh, a thread is runnable, or in fact has the thread died. I mean, it's possible to do that. I mean, it might be important for you to find out. It's alive if it's either running or runnable. So is alive will return true or false. Yield, it's a void. It doesn't have a return value. I'm saying it's a static method, and I'm afraid you'll have to wait for a bit of an explanation of what the static prefix means. But for the time being, it just means that it's a class method. It belongs to the class, and if the yield method is executed, it will affect all instances of the class, all objects that have been created from the class. But what yield does is to cause an executing thread to yield to others. If there are other runnable threads, these are going to be scheduled next rather than the thread that's called the yield method. And two more methods, suspend and resume. I've mentioned those already. Suspend suspends a thread execution. The thread is stopped being runnable and it's not running. And resume resumes a thread that's been suspended. And in general, if there is a method to put some thread into a blocked state, whatever that blocked state has been caused by, there is an inverse that puts the thread T back into the runnable state. So sometimes it's necessary to explicitly allow other threads to execute their run methods. One way of accomplishing that is simply to put yourself to sleep. Alright, there's a thread method, a method that belongs to the thread class that allows you to put yourself to sleep. Allowing, which has the consequence, of course, that allows other threads to run. But you can't actually determine which of the other waiting threads will run. And for example, a thread might be very compute intensive. It's doing a great deal of work, and maybe it's using a lot of resources, whether they be memory resources or internet sources or whatever, very greedy. So one way of handling that is to use the static method sleep. Sleep takes an integer representing the number of milliseconds and nanoseconds to sleep, and when this executes, this thread changes state and can't execute in this sort of sleeping state, and so is placed on the queue of sleeping threads, each of which is waiting for a period of time to elapse. And note also that the sleep method can throw an exception, so the sleep method invocation must be wrapped up in try putting a particular thread to sleep, and if anything goes wrong, try and catch the exception. And we're going to learn a lot more about exceptions in the very near future, so don't worry too much about that. But Java just simply marks many of its methods as capable of causing an exception. And a classic, I mean, perhaps a very easy to understand example is that something going wrong is that if you try and open a file to read it, the file name doesn't actually name a file on the system, a thread, an exception will be thrown. So the wait method, if the thread calls this, then the owner of the monitor on whose availability the thread is waiting, think of, just for the time being, think of monitor as a lock on whose availability the thread is waiting, must first of all call notify or notify all. Wait, when called, releases a lock on an object, usually having gained a lock via executing synchronized code. And I say more about that on page, I think a bit later on, not sure about page 27. If another thread obtains the log, it is said to own the monitor and should call notify, which will enable the first thread to regain the log. So this should remind us very much about the use of semaphores and the wait operation and so on. You know, if a resource shouldn't be used unless it's with the greatest care, you could go badly wrong. And I'll give you a little example of what I'm talking about a bit later on. If a thread is blocked because it's waiting for an I/O completion, then the operation must first complete for it to become runnable. Okay, so that's all a bit long-winded, but reasonably clear. I mean, all I'm doing here is to introduce you to some important methods that relate to thread control. A dead thread might occur because a run method finishes, or I'm actually telling that thread to stop. So stop throws, executing stop on a thread can throw or will throw a thread death exception to the thread object. Once a thread passes such an object to its base class, the thread dies and the mess will then be cleaned up. So the details aren't too important at the moment. At the moment, we're not likely to want to use the stop method. We don't unlikely to want to kill or make a thread deliberately die. So, but it's just there for the notice. Let's resume the examination of the two main ways of defining or declaring and running threads. So you could create a thread, first of all, this is the case that I'm most interested in. You create a thread by extending or subclassing the class thread. And what we do is to put all the code intended to constitute the thread's behavior, the thread's functionality, what the thread does. It could be anything. You name it. I'd probably be able to design some Java to represent a particular functionality that you want. The description of the thread's behavior, or what we want it to do, within a run declaration in the subclass. And this, as I'm sure I've said to you already, this has the effect of overriding thread's own empty, abstract, vacuous run method, which has been inherited by the subclass. But the disadvantage with this general technique of thread creation is that you might wish to create an extension of some other class rather than just thread. And you might simply want to add some code that uses such and so methods in the existing class that have been inherited, might make life very easy, prevents you from having to write your own equivalent code, which could take months. But you might also want to make the subclass, you want to use a thread in the subclass, in which case you cannot, Java isn't going to allow you to do this. So I'll just show you this diagram. So here's my class, and it'd be quite nice if I could subclass this class, which is called extendable class, for some class. It might be full of useful utility methods. I want to use those in my new class. Maybe I want to do some pretty advanced mathematics in my new class. And there's a library, in effect a library of useful functions I want to use to do the processing. But I also want to create a thread in my new class. I want my new class to represent one or more threads. Uh, and naturally, I think I would think about extending the system thread class. But Java says, no, 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 that's not allowed. You're not allowed to do that. You can't inherit from two parents. All you can do is to inherit data, variables, and methods from a single parent. So we've got to think a little bit about how to overcome that. So that's what I'm saying here, okay, verbally in my notes. So what we have to do in that case is to create a thread using what I described as the runnable interface. And, well, let's understand what an interface is. Its declaration is very similar to declaring a class, and it might contain constant declarations. For example, it might contain pi equals 1 4 blah 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 to the first decimal places in the infinite decimal expansion of pi. Or it might contain c equals the speed of light represented in kilometers per second. Or, or the interface might declare one or more abstract methods. And in other words, it may declare for example, the return values of methods, but without supplying a body or implementation of those methods. They just just don't exist. You haven't got the curly brackets. Nothing is said about the definition of the methods. And it will be up to the subclasses or other entities to implement those methods. And interface just tells you what constants methods will appear, not how not how they are implemented. So typically a class will be used to implement an interface. So for example, that class in implementing an interface perhaps can use any of the constants declared. It can use any of the abstract methods declared. Perhaps some of the methods aren't abstract, they are actually given um, uh, uh, some kind of implementation or definition. But interfaces can themselves have super interfaces. One interface can extend another, be a subclass of another. The one that is extended is the super interface. So, um, um, so let's have a look at this example of an interface. And because one of its methods is abstract, the interface itself is abstract. What does that mean? Well, I'm talking about Runnable, of course. This is it's public abstract interface, and the Java system calls it Runnable. Curly bracket, curly bracket. So it's a bit like a class definition, but it's not because I'm defining an interface. One of the methods it contains is this. It contains run. Run doesn't have a return value, so it doesn't return an integer like the square root function, for example. The return value is actually, it's abstract. It's an abstract method. We don't know what run returns. It's actually we've actually said it returns void. It doesn't have a return value. Sorry, perhaps I hope I'm not contradicting what I've just said. So run is an abstract method. Oh, the question is, why? Why is it being marked as abstract? Look, here, there's no curly bracket. And telling, there's no Java code here, end of curly bracket. It's not telling you what run does or how it does it. Completely blank. It's just, all you're getting really is the name, run, together with the fact that it's void. and it's characterized by the fact that there's no body, there's no definition behind it. And the same goes for any other abstract interface. All right, there's one or more methods haven't yet received a definition, and it's up to the class that implements the interface to give those methods definitions. So Java allows us to implement the runnable interface by implementing Runnable's abstract method run within the subclass, within a class or subclass. So once this is done, we can then create a thread object from the runnable object by passing the object to one of thread's constructors. I mean, that sounds like a bit of a nightmare to understand. But what we could do is that we could create a thread, no problems, using our class that let's call it Kindberg, which implements Runnable. And all I have to do in the Kindberg class is to give run the behavior that I want the thread to have. Maybe it's just displaying images on the screen. Whatever you want it to do, you put that in the run. You implement the run method. But to create a thread that can to create an actual thread object from the runnable class and from the object, from the class that you've just used to implement the interface, to get which is called a runnable object, what you need to do is to pass this runnable object to one of thread's constructors. Well, okay, have you forgotten what a constructor is? I'll tell you, once again, I've documented it in my presentation on objects. A constructor is a method, like a method. It's very similar to an ordinary method. It has the same name as a class, and the code relating to the constructor will be executed at the moment that you create an object from the given class. Alright, so once you've passed the runnable object to the thread's constructor, you will get an object that can be started. And what I mean by that, you can start the run method in your subclass to start executing. You can start it executing. So let's have a look at this. I've got my new class. That's my name for a class. It extends. I'm just going. Hang on. Let's just have a look at this. So what's going on here is my using. Here I've got the runnable interface, and I've got my new class is going to, first of all, it's going to subclass extendable class, and then it's going to implement, I'm marking that with a green line, it's going to implement this interface. And this is all allowed. Okay. So my new class can, if I want it to, it can subclass some other class. This class can then implement, perhaps by my writing a run method in this class, I can actually implement this interface. I mean, hopefully that's not too clear. What I can say is my new class extends, it's a subclass of extendable class, and because I'm putting I'm defining a run method here, I'm actually implementing the abstract run method I find in the runnable interface, which I've just spoken about. So just a bit more, tiny bit more work to do. Right. So the neat thing here is that we can implement Runnable's run method in my new class using perhaps all the useful methods I find in uh, the superclass extendable class. I mean, remember, uh, my new class is simply going to be a subclass of extendable class. Right. Uh, Note well, the programmer must implement the run method in my new class. So let's just backtrack a little bit. How precisely is an instance of the thread subclass created here? Well, think a little bit. Okay, so in the first case, we're going right back to the beginning, the first method of creating a thread. My new class extends thread, so we're not implementing the runnable interface here. What we're doing is simply subclass thread. Then I can give it a name, my thread, which is the result of creating an object from my new class. Okay, so let's just look at this one more time. This is my class. It's called my new class. I'm subclassing thread. In my new class, I've got a run method which I've defined. Now, to get a thread from all this, what I need to do is to create an object from my new class. How do I do that? Well, you say my new class. That returns an object, and I'm going to assign that to this variable, thread variable, or variable of type thread. So my thread is going to be that object. So, I think I'm just repeating myself here. Yeah. So what I'm doing here is what I've just said I'm doing here. We create a specific my new class object of type thread by writing this line. So I'm explaining what's going on here. So the expression returns an object of type thread, and once we've got that, um, I put the new object my thread into the new thread state. Okay, and to start the thread I've created, I write my thread. Because remember, that's the name of the thread I've just created, and it's a class which contains a run method. Why? It's because I've inherited run from the thread superclass, and I just write start, and execution will take place immediately, and I can, if I wanted to, I can create another instance by writing my thread.start, second thread, identical to it. Okay, so we've spoken a little bit about Runnable, and what we've got is something called my new class, which implements the Runnable interface. That's fair enough. Hopefully we all understand what's happening here. Point about the meaning of implementation here is that my new class contains a method. It contains the run method, which I've actually inherited as an abstract method from Runnable. So, this is the only tricky bit in the whole of the presentation. It looks tricky, it's not actually tricky. So what I can do is to create a runnable object from my new class. Remember, my new class implements Runnable, and it's going to be of type Runnable. When I create an instance of this class by using the keyword new and give it a name, then mine is a new object which results from my new class. fits. It has all the properties of my new class, and mine is certainly of type runnable object. And what I finally need to do is to plug mine, which is the name of the object I've just created, into threads constructor. So that's how I do it. And I'm going to say that my new thread is a type thread, and it results from creating a new object from the class thread with this runnable object plugged into its constructor. So that does look complicated, but it's not. You remember, a constructor is often used when you want to create an object. As a matter of fact, the thread class enables you to convert a runnable object into a fully fledged thread, and I'm calling it my new thread, by plugging the runnable object into threads constructor. So that's why I've got lots of exclamation marks. And I've got some program examples that use this technique of creating a thread. So to put these two thread objects, my new thread, which is what I've created here, and my thread, which I created on the previous page, into the runnable state, we write the following. So what I'm showing you is how to create running threads of the two sorts that I've described. So my thread originally was a subclass of thread, and my thread was actually a new instance of the class that subclasses thread. My new thread results from creating a thread from threads constructor by plugging in a runnable object. In both cases, I can start the run method to execute by writing dot and the name of the thread method, start. My thread contains, because it's a thread, the start method. I can use it. What does it do? It just executes the run method. So the example I've got, which creates three threads, I think you can find it, is this example, which I've already, it's already on Pharos, and if you notice carefully, I've got raving is a subclass of thread, and I'm using raving's constructor to initialize these two variables. So I want to plug in a pause time and a particular word, what. Here's my run method that I've inherited from thread. What do I want it to do? It's very easy. Forever, print out the word I plugged in, and then simply go to sleep for this amount of time. And I have to wrap everything up with a try-catch clause, but I'm not going to comment on that too much at the moment. So that's the end of the run method. And here's my main method. Oh no, I don't want to go down. Oh dear. Right. Let's just do a rewind. Bear with me. So here we are. Sorry it's taken so long to do a rewind. So here's the main method, and so it's a public static void main, and I'm creating three raving objects, and I'm using different. Uh, so I'm using three sets of parameters into Raving's constructor. First is Chris with a pause time of 20. Second is Kinberg with a pause time of 100. And the third is an exclamation mark with a pause time of 150. So I'm creating three new thread objects. They're all the same, apart from what they're actually doing in terms of these parameters. One's going to print out Chris, wait for 20 milliseconds, then do it again. Kinberg's going to print out Kinberg. This raving object is going to print out Kinberg and wait for 100 milliseconds, and so on. So here is quite a nice illustration of the use of a class that subclasses extends thread. And once again, you're probably sick to death of me saying this, because raving is a subclass of thread, i.e. raving extends thread. Raving inherits the run method. I've defined a run method. I've defined what I want to happen, and I'm making use of Raving's constructor here to allow me to alter the behavior of each of the true thread objects that I'm about to create, and and uh, and hopefully you understand this. New Raving Chris 20 is actually I could have assigned this new object to a thread variable called t1, but I'm not going to. And then I could have said t1 dot start the thread t1. What I'm doing is this. Watch the cursor here. This expression returns an object, a new thread object, and just placing the full stop dot start after it to get the run method executing. So what have I got to say here? I mean, the lines above are equivalent to lines of the form X is of type thread, and it results from creating a new raving object with these two parameters plugged in. And then, this is a second line, I start X. So I could just compress these two lines into one, this line here. So hopefully that's reasonably clear. So, okay, I've got a runnable interface example, and so here I've got a class called ChitChat that implements the runnable interface, and again I can use the constructor for ChitChat to plug into parameters like what do I want to be output, and after what period of time do I need to wait. So have a look at this. And here's my run method. I print out the word, and then I use thread.sleep pause. So I'm using the sleep method with pause plugged in to specify the time I'm to go to sleep. And what I can then do in my main method is to create Pong, which is a runnable object. Pong is a runnable object, and it results from creating a new instance of the ChitChat class, which you remember implements the runnable interface. And I can create a second runnable object called ping from ChitChat. And what I can do in these two lines is to plug in Pong and ping into the constructor for thread to give me a fully fledged thread. And when I've got that, I can simply start it. It'll start executing Pong's run method. And I could have written something like, I don't know what I was right. Yeah, sure. Not sure about that. Just ignore that comment. These are the two important lines. So let me just make one observation here, is that public static void main is actually runs as a thread. So all these statements are executed in sequence. Let's have a look at this. This is going to be executed in sequence. It's a line, Java code line. Sorry, it's a line of Java code that actually starts Pong's run method up. And as soon as you do start it, I'm able to execute the next line. So at that instance in time, I've got this thread running at exactly the same time that the thread I've called Pong is running. And next line is I can start ping up. So I've now got 3 threads running, all concurrently. And what I'd like you to do is to simply cut and paste these 2 multi-threaded programs and see what happens, and we can discuss their behaviour on another occasion. And I think that's what I'm referring to be the first laboratory task. A little bit of homework. And I'll finish off within 10 minutes. I'm just going to talk a little bit about synchronization, thread synchronization, because I think it's pretty important for you to understand this. To ensure mutually exclusive access to resources, you can synchronize methods or place some kind of synchronization lock on an object to gain that guarantee of mutual exclusion. So if you remember, we did spend quite a lot of time in thinking about mutual exclusion and how semaphores can guarantee mutually exclusive access to possibly a non-shareable resource. So if a thread invokes a method that's been marked as being synchronized, the object is said to be locked. And if a method is marked as synchronized, then 2 or more method invocations are serialized. You can't have them both taking place in the same window of time. For example, if a second thread attempts to access an object whilst a first thread has access, the second will be blocked until the lock is released. A good reason for not having public or protected data is due to the risk of unsynchronized access. I mean, if I've got a couple of methods and they're not marked as being synchronized, then 2 threads could execute those 2 methods which might have conflicting outcomes on the data I have contained in my object. A data field should never be concurrently written to and read from because the outcome's unknown. And what are called class methods can be synchronized using a class-wide lock for that class. What I really mean is that if you've got Methods that are marked as static, they can also be synchronized. And if a method is static, the method, the uh, synchronization is going to affect any object that has inherited those methods. In other words, any subclass might have inherited methods A and methods B. If they're both synchronized, it's not possible for two threads that are being created from that class to execute those two methods simultaneously. So I spoke about placing a synchronization on an object. What I can do is to write the word synchronize in front of some expression that stands for an object. Then I can specify a block of statements, and all I'm saying is that it's not then possible for two threads to simultaneously execute this statement block. I mean, if I've succeeded in synchronizing on a particular object, then another thread that attempts simultaneous synchronization will have to wait. So I can do what I want to whilst I've got the lock, an object lock on that. So a little example, and then I'll probably finish, because I've only been speaking for an hour. Right, here's a little example where I've got a method called transfer, and I'm synchronizing it, so it's within my class. It's marked as being synchronized, and it takes three parameters. It's the number representing an account from which I can take money, and the second parameter is an account number which represents the account to which I'm about to transfer some money, and the third parameter is the amount of money to be transferred. And what I can do is this. While there's not enough money to move this amount from the from account to the to account, I need to wait. And the action of waiting is simply means that I am temporarily losing the lock on the transfer method, and another thread could go ahead and use the same method to go ahead and transfer, because there's no lock, it's been released. So let's supposing that you come along, you put lots of money into your account, and then you execute a notify command. You don't have to do a wait. You simply end up notifying me that you've finished using the transfer method. In that case, I will be woken up, and one thing I should do, because I'm in a while loop, I've been woken up, I can check to make sure there is now enough money to transfer into my account, and I do it, and then I can notify. Well, in fact, when I'm woken up, I regain the lock on this the use of this method. So if I do the transfer, what I can do is to notify all other threads that might be waiting. Or sorry, I'm letting it be known that I no longer have the lock on the transfer method. So in this way, it's not actually possible for two different threads to come along and use my method to transfer money into or out of their accounts. and at the same time, that is, and it gives us an element of mutual exclusion, which is highly desirable in this and other situations. Well, the document goes on a little bit, um, and you might wish to just have a quick look at what I'm talking about, and you might just give a little bit of thought to this document where I'm actually implementing class threads run method directly, and I'm creating a new thread from the class thread, calling it T, and then start. In fact, I'm not starting it here. I'm running it, so it's a bit of an oddity. There are cases where I can actually use the thread method's run to actually start the run method. So it's all a bit. It's quite a rich area of complexity, some complexity. So, but I will finish there, and thank you very much for listening. But it is a hasty substitute for the recording I lost the other day. So, many thanks. Bye bye.